Hey everybody, so this is going to be a quick video on beginning our coverage of the mechanical senses. In this video, we're going to start on the first mechanical sense, probably the mechanical sense that we are aware that we use. Uh, it's one of the two senses that we're most aware of, hearing. All right, so let's get right to it. So, um, when we talk about the mechanical senses, we're calling them the mechanical senses largely because they all perceive uh, mechanical activity, meaning they all perceive that their receptors work by perceiving movement of the receptor, or some part of the receptor cell. So, for example, hearing, which is responsible for auditory sensation, hearing it occurs because of the movement of cilia on the auditory receptor. Touch sensation is a mechanical receptor. Those receptors become active when the receptors are physically altered, meaning by pressure or something changes kind of changes the shape of the receptor's membrane. So both tactile perception and really you can kind of in the majority of somatic sensation is also a mechanical sensation. But again, here we're just going to focus on hearing, and the videos that I'm going to be posting today are going to only focus on hearing, and then we'll start talking about the other aspects of somatic sensation. So, let's talk about what physical energy we're sensing when we hear. Because again, sound, the part that your brain makes up, is caused by mechanical changes. Again, specifically the movement of your auditory receptors. But what causes it to change? What causes those auditory receptors? Specifically, changes in air pressure. All right, so anytime you have a medium, and that medium could be air, water, right? It could be a wall. Okay, anytime you have a medium, something for something that has molecules, and you have alternating densities of pressure. It can be very, 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 very small changes in density, where the molecules come together and then push apart, come together, push apart. And so when you have these alternating sequences of rarefaction, meaning they get spread out, and compression, meaning they get pushed together, right? You get a vibration, and that vibration changes in pressure, okay? Again, in air, then it's air pressure, all right? Anytime you get a vibration like that, you get, when it enters, when that change in pressure enters your ear, it, through a series of events, which we're going to cover, it literally pushes the hair cells back and forth, all right? So that movement of the compression and then followed by refraction pushes the hair cells one or the other. So if there's an area of compression over here, the hair cells are pulled in that direction. If there's compression right here, there's rarefaction right here. And then when the rarefaction moves over here and the compression moves here, the hair cell gets pulled back this way. So the hair cell gets pulled in the direction of the compression. Now I know a lot of that is kind of doesn't make a whole lot of sense right now, but hopefully it will make a little bit more sense in a little bit when I show you how we plot the physical qualities, the changes in it. But again, the physical energy that we perceive is that causing what we perceive as sound is changes changes in pressure, regardless of whether it's air pressure, water pressure, the pressure of the medium. Now, one thing that's cool to me, because I'm a dork, all right, is that if you don't have a medium, you don't have sound. If you don't have a medium for changes in pressure to pass through, you can't. Then nothing can move your auditory senses or your auditory receptor cilia, and so you can't hear. Um, so I forget. I feel like it's from Star Trek or some other equally nerdy thing that I enjoy. Uh, I remember the phrase, "No one can hear you," or maybe I read it. No one can hear you scream in space, and that's true because space is a vacuum. There's no medium. That's what a vacuum is. It's the absence of molecules. So because space is largely a vacuum, there's no medium for changes in pressure to pass through. And so no one can hear anything in space. So in the movies when, like in Star Wars, right? When the Death Star blows up and you hear the explosion, right? You wouldn't hear it. It would be if you were hanging out in space in a spacesuit and it went off, you wouldn't hear it. Now, when the shock wave hit you, then you would hear it, all right, because the shock wave is pushing air and essentially pushing the medium out, all right. And so when the shock wave hit you, then you would hear the explosion. But until that, I mean, you wouldn't even hear the, right? It would just be, all right, because there's no medium for that sound to pass. Again, cool to me, maybe not to you. Hopefully. Now, the perceptual experience that our central nervous system creates to represent these changes in air pressure is so like I said, you know, your brain makes a lot of stuff up, which I think is freaking cool. But sound is one. Sound doesn't exist outside your head, just changes in pressure. Now, let's talk a little bit more about those physical qualities. So remember that the physical energy that we perceive as sound is pressure changes in or fluctuations in pressure. Now, the majority of the time, because the majority of the time we're hanging out in air, it changes in air pressure. Now we can plot. Now, well, before I get into that, remember that what I told you that the changes in air pressure are you have these alternating bands of compression where the air molecules are tightly packed together, and rarefaction, where the molecules are kind of pulled apart. Maybe a useful analogy is a wave. So think about when you go to the lake or when you go to the beach, right? And so you're sitting there on the shore and you notice that the water keeps coming up and then moving back. Keeps coming up and then moving back. Moving up and coming back. Or moving back. Well, note that when it moves back, you look out into the water, you're going to see crests. Crests pull up, right? And then when the water comes back further on the shore, those crests flatten out. So, well, really what happens is the wave just travels. But right before the wave gets to you, the water right at the shore pulls back, right? And then the wave crashes. And then when the next comes up, the water on the shore pulls back and the wave crashes. Now, what's happening? Well, the way a wave is created is by water from the surrounding areas in front of the wave and behind the wave being pulled up, okay, being pulled up into the wave. Well, you can kind of think of that wave as the area of compression because the water is becoming denser in that spot where the wave is. And then in front and behind it, the water is becoming less dense, spreading out, the areas of rarefaction. Well, the same thing happens to the air molecules, right? So when I'm talking, well, when you're listening to this, what's happening is that speakers pushing out the sound. Well, what it does, what most speakers do, is if you've ever, especially if you've looked at a really big speaker, all a speaker does is this. It moves in and out. That's it. That's all a speaker does. And what it's doing, it's creating, when it pushes out, it pushes the molecules the air molecules right in front of it. It smashes them up against the air molecules in front of them. When it pulls back, it pulls the air molecules back, and so it spreads them out. And so as the speaker pushes in and out, it's creating alternating patterns of compression and refraction. Compression and refraction. Now we can plot that change in air pressure with the sine wave. I'll show you sine wave in a little bit. But two features about that sine wave that we tend to measure and look at the relationship between those qualities and our perception of sound are the amplitude of the wave. I'll describe what that is in a little bit, and the wavelength of the wave. Right. So here is an example of a wave. So here's your sine wave, and here's what's actually happening. Okay, so remember the condensation, what I was calling compression, literally the same thing, and then refraction, right? So wavelength is just exactly what it was when we were talking about light. It's the distance from one crest to one crest, or from one trough to one trough, as you can see there. Now, the other physical quality is amplitude. So it would be the height of this wave and how deep the trough is. Now, the wavelength is dictated by how quickly the rarefaction and condension alternate. Right, so you can see that in the point of condension, this wave goes up. All right, and then in points of refraction, it goes down. Well, if there were, imagine there was another condension right here, another one right here, and another one right here. Well, that would mean that this wave would go up, down, up, down, up, down, up, down. And so the wave, there would be a shorter length between the waves, between the crests, and a shorter length between the troughs. That changes the wavelength. Now, we also have a difference in how compressed and how spread out the molecules are when condension happens and rarefaction happens. The more condensed the molecules, the greater the condension. And the more spread out the molecules, the greater the rarefaction. When there's the greater the condension, the higher pressure. And the more spread out the rarefaction, the deeper the trough. And so that's what creates amplitude, or that's what changes amplitude. So, various sounds compress sound, air molecules more than other sounds. So, a jet engine is going to compress air molecules far more than my voice, okay, or your, ringtone or whatever, okay. So the more compression and rarefaction there is, the more molecules, the more densely molecules are packed, and then the more spread out they are, the greater the amplitude. Okay. Now you can have a very high amplitude, short wavelength. All right. So it's the compression and rarefaction. There's a lot of compression, a lot of rarefaction, but it's happening really fast. So it's super condensed, super rarefacted, super condensed, super rarefacted, as opposed to a very high amplitude but long wavelength, which would, it'd be more like super condensed, really rarefied. Super condensed, really rarefied. So you notice how I went slower the second time than the first time. Because the first time, the wavelength was shorter because those alternating points of condension and rarefaction were alternating faster. All right. Now, both of these physical qualities, amplitude of the sine wave and pitch of the sine wave, correspond approximately to the perceptual quality of the sound, specifically amplitude. So how compressed and how spread out the air molecules are roughly corresponds to how loud we think or we perceive the sound to be. And I say roughly for a reason that I'll cover here. And then the wavelength roughly corresponds to the pitch we hear. So how high pitched it is, it's a really high pitched, or really low pitched. All right. So the wavelength tends to correspond to the pitch we hear. I think this was on a previous slide. We typically measure amplitude with decibels and wavelength with hertz. So think about when you're turning up, if you've got a sound system or even in your radio, you know, the numbers go up, although the numbers aren't always decibels. As you're turning it up in decibels. If you have one of those sound systems that actually measures it in decibels, as you turn it up, it gets louder. Amplitude is measured in decibels. Now, I say that amplitude is approximately associated with loudness because we have this really cool perceptual feature where we don't hear all frequencies as being equally loud. Okay, so this green line here, this is what we call the audibility. Anything below this, we flat can't hear. All right, so we can't hear a 100 hertz sound at 20 decibels. We can't hear it. Now we can hear a 500 hertz sound at 20 decibels. Why is that? Also, just because decibels are higher doesn't necessarily mean we perceive it as louder. So for example, if you were to compare a 100 hertz sound at 40 decibels and a 1000 hertz sound at 40 decibels, the 1000 hertz sound would you would perceive it as being much louder, right? Now why? Why is it that we have this odd audibility curve? Well, why is it that we can hear some sounds when they're much quieter than other sounds? Well, one of the really neat features is this really neat feature is caused by the fact that we have a tunnel. Our outer ear is involves an ear canal, and our ear canal creates a closed-in tube. Okay. Now, what that does is when the sound comes in, right? So the air pressure comes in, the sound wave comes in. It hits the back of your eardrum. Well, that sound, I mean, think about it, most of it, like right now, you can probably hear a little bit of reverberation. Well, reverberation, all that is the air pressure hits a surface and then bounces back, okay? That's what's happening inside your ear. So the air pressure comes in, hits your eardrum, and then the eardrum bounces a certain wavelength back. What happens is this really cool phenomenon known as resonance. And I will show you in class a kind of a video of resonance. I did incorporate it into this particular slideshow. But basically, imagine two sine waves, okay? One moving left to right, and the other one moving right to left. Now imagine that these two sound waves are the equivalent frequency. Okay. Well, remember that a sound wave is just condension and refraction. So when the sine wave of the sound wave goes up, there's greater condension. When it goes down, there's greater refraction. Now, if these two waves are going in opposite directions, right, and they cross each other, then when the 2 points of condension match up, then you get kind of like multiplying. The condension is multiplied. So whatever the the condension of the first sound is multiplied or added to the condension by the other sound. And so when they cross, it's not just the convention of one wave anymore, it's the convention of both waves added to one. So the convention is increased. Well, and then in the rarefactions, not only of the sound wave where you have molecules spread out from one sound wave, when the two cross over, they add up again. And so, or I guess they say they subtract from one another. So now it's not just the rarefaction of one wave or the other, it's them together. And it spreads them out even further than one wave did by itself. So when these two waves become completely, so imagine that these were three waves, right? So when they become, my three fingers, get three fingers up on each for those, so for when I make this. When the three fingers are in perfect alignment, meaning that the three fingers completely line up, right? Then you get that addition. So the convention of both waves adds up, and the refraction of both waves is multiplied too, and it goes down, right? So remember that when if you were to compare an area with low convention, a sound wave with low convention to a sound wave with high convention, the sound wave with high convention is higher in amplitude, and so we perceive it to be louder. So what happens when you have two waves cross over and they multiply each other's effects? They increase the amplitude. That's resonance. And so when you have two waves that are equal in frequency crossing one another, the more they line up, the more they amplify one, the greater the resonance. The more they map up, the more they were equal in frequency, the more they amplify. And so that amplification is a product of resonance. Resonance is the mapping up or matching up of two different sound waves. Well, when the sound wave comes in and it hits your ear and your ear starts reflecting sound back, it only reflects a sound at a particular hertz, and that the frequency of the reflected sound is determined by the length of your ear canal. And because of the length of our ear canal, the average resonance frequency of your eardrum is about 3,000 hertz. So it's always sending back 3,000 hertz. Well, the sounds coming in are of all various frequencies. Wavelength is the frequency. So, you have various frequencies. The further away the incoming sound is from 3,000 hertz, the less resonance you get, because, again, resonance is when the sound waves map up, when they match up. Well, if you've got a 5,000 hertz sound coming in, that matches the 3,000 hertz sound being reflected less than a 4,000 hertz sound coming in, and especially a 3,000 hertz sound. So if a 3,000 hertz sound comes in, and then a 3,000 hertz sound is being reflected by your ear, those two match up perfectly, which means they have close to ideal resonance. And so that 3,000 hertz sound, because of the resonance, it's amplified. It sounds louder. The further above 3,000 hertz you get, the less resonance you have and the less amplification you have. So the lower, the further below 3,000 hertz you go, the less the resonance, the lower, the less the amplification. And so here, if we go back to this audibility curve, right, notice that we are most sensitive to sounds around 3,000 hertz. It doesn't take much for us to hear a sound at 3,000 hertz. Why? Because an incoming 3,000 hertz sound resonates with the 3,000 hertz sound being reflected by our ear, and it gets amplified the most. As that incoming sound grows higher, than 3,000 hertz, resonance drops off and amplification drops off. As that incoming sound drops below 3,000 hertz, resonance drops, amplification drops. So that's what creates this nonlinear audibility curve. All right? And it's reflected at all higher hertz. All right, so these are equal loudness curves. What that means is that any point along this line, these lines are experienced as equally loud because of resonance. So a 100 hertz sound played at 60 decibels sounds equally loud to a 1,000 hertz sound played at 40 decibels. All right? And that, friends, is as far as I wanted to go with this video. So this was a discussion over the perceptual and physical qualities that generate of the physical qualities of the stimulus and the resulting perceptual qualities of our perception. As always, if you have any questions, let me know. Otherwise, see you later.